So in this video, we're going to just give an overview, kind of introduce undetermined coefficients, but give a little bit of background as well. So we've been solving homogeneous differential equations, and we're going to need to shift gears and solve non-homogeneous differential equations, and we've been focused on second order linear differential equations. So things that look like a y double prime, b y prime, plus c times y equal to 0. So homogeneous differential equations. And in the first video for second order differential equations, we called the solution to the homogeneous equation the complementary solution. And then we said that, hey, if we wind up with a function where it's equal to g of x, where g of x isn't 0, then if we find the solution to this, it's called the particular solution, y sub p. And then we identified that the solution to the differential equation was going to equal the complementary solution plus the particular solution. And I want to kind of geometrically get you to think about this in terms of something you've done in calculus. So in calculus, we've found equations of lines. So you get some sort of line out here in 3 space. And the technique for finding the equation of the line is we found a vector that's parallel to the line, and it didn't matter what vector it was. It could be any length, point either direction, but it did have to be parallel. So as long as we had a parallel vector, let's call it ABC, we multiplied that parallel vector by a scalar k so we could stretch it parallel to the line to any length or direction that we needed. But if this is all that we did, what we would get is a line parallel to this line that contained the origin, the point 0, 0, 0, right? And if we let k equal 0 here, we'll get the origin. And so the idea is this line is a vector space from linear algebra. It's a vector space. It contains the 0 vector for R3. The origin is the 0 vector for R3. And this wasn't enough to get us the equation of a line. This gives us the equation of the line that contains the origin. And then what we did next to find the equation of a specific line, because remember there's infinitely many lines that are parallel to the vector ABC. What we did to get a specific line is we found any point on the line, and it didn't matter what the point was. It just needed to be a point on the line, and we added a vector that got us from the origin, the 0 vector, to the line. So if I call that vector v, we add the v on. And so what we want to recognize is that what we did in calculus to get the equation of our line is exactly this idea right here. Find the complementary solution. Find the solution that contains the 0 vector in the vector space, but then find some particular solution to the non-zero equation so that it gets you from the 0 vector to the actual object that you want. So that's the idea. That's what's going on when we find the solution y equals the y complementary plus y particular. We're finding with the when we solve the homogeneous problem, we're getting a vector space. Our solution space is a vector space. But then when we have a driving function, this is called a driving function, that isn't equal to 0. Did I spell that right? That's horrible. Driving function. When we get an equation not equal to 0, then we need a vector, a particular solution that gets us from the origin or the 0 vector out to the actual object that we need. So we're going to now focus on solving homogeneous linear differential equations with constant coefficients when we have a driving term that isn't equal to 0. And the solution process is going to be, well, first set your differential equation equal to 0 and get the complementary solution. Find the solution to the homogeneous equation. And then what we're going to want to do is find a particular solution that solves the non-homogeneous case, and we take the sum of those two solutions to get the solution for the non-homogeneous case. And the technique that we're going to be looking at is the technique of undetermined coefficients. So somewhere in here we go. We're going to be looking at a specific technique, the technique of undetermined coefficients. And this technique only works for linear differential equations. It will work for linear differential equations of any order. We're going to be focusing on second order linear differential equations initially with constant coefficients because that's what we've been playing with. And the idea behind undetermined coefficients is that if you have a function g of x, if g of x has a form for which the derivatives of g of x have the same form as g of x, then we can guess that the form of the particular solution that we need is going to have the same form as g of x. So for example, if we have a polynomial ax squared plus bx plus c, when we take the derivative of a polynomial, we just get more polynomials. The derivative of a polynomial is a polynomial. So if g of x is a polynomial of degree 2, what we're going to guess is that this particular solution will also be a polynomial of degree 2. And then undetermined coefficients means we need to figure out what these guys are that give us the particular solution. We know that what we're going to know is that, hey, if the solution is a second degree polynomial, if the equation is equal to a second degree polynomial, the solution is probably going to be a second degree polynomial, but we need to figure out the values for a, b, and c that solve the equation. So undetermined coefficients is going to be a technique that we use when the function g of x has derivatives that also look like g of x. And that's going to occur in very specific cases. Polynomials, derivatives of polynomials are polynomials. E to the alpha x, base e exponentials. When you differentiate e to the crap, you get a constant times e to the crap. So the derivatives of e to the x or e to the alpha x, they look like e to the alpha x. So we can say, hey, if the driving function is an e to the alpha x type of a thing, it's probably going to be the case that the particular solution to the differential equation will have the same form. And it's also going to work for the sine function and cosine function, because derivatives of sines and cosines give you sines and cosines. So what we have is, if g of x, if the driving function has certain forms, we're going to be able to guess the form of the particular solution that we need to move that homogeneous solution out into the correct position. So this right here, I'm going to put this, which is some common guesses that you make depending on g of x. I'll put this directly into the homework assignment so that you don't have to copy it down off of this slide. And then in the videos that are going to come up, what I'm going to do is look at specific cases of g of x and go through the solution process, the guessing process, where we come up with the coefficients that solve the differential equation. So we'll do a series of specific worked examples.